This flash of lightning can be seen from a great distance and is quite dramatic. The ignition of this gunpowder in this cannon can be seen and heard, as can the striking of a match bursting into flame. But less dramatic are the changes occurring in this metal as it turns orange, or the changes going on among the different chemicals found in the seawater and the surrounding air, as well as the hundreds of changes going on in these flowers that are not visible to the naked eye. These all involve changes referred to as chemical reactions. A chemical reaction is the process of one or more substances converting to form new substances with different properties. During the next few minutes, we are going to explore chemical reactions and some of the different ways chemicals change to form new substances. In chemical reactions, a new substance is formed from chemicals interacting with each other. For example, we generally think of leaves on trees as being green. However, at certain times of the year in some places, leaves turn bright, vivid colors, the result of chemical reactions. Another easily observable chemical reaction occurs when the chemicals found in this match head are ignited into a flame. When extinguished, this black substance is left, a very different substance than the red-colored chemical substance that existed before the match was ignited. In chemical reactions, there are two classes of substances: those substances which are present before the chemical changes, and those substances which are formed by the change. Reactants are substances that enter a chemical reaction. In this reaction, baking soda, also known as sodium bicarbonate, and vinegar or acetic acid are the reactants. When combined, they produce new substances called products. Products are substances that are produced by a chemical reaction. The products produced in this reaction include carbon dioxide gas, sodium acetate, and water. Not all substances undergo chemical reactions. For example, when this rice combines with this candy, a chemical reaction does not occur. The original substances were not changed and no new substances were formed. It is possible to describe a chemical reaction in words. For example, we saw how sodium bicarbonate and acetic acid chemically react to form carbon dioxide gas, sodium acetate, and water. Scientists had developed a simpler way to present a chemical reaction. Using the chemical symbols for compounds, a reaction can be expressed by a chemical equation. A chemical equation is an expression using chemical symbols to represent a chemical reaction. In a chemical equation, the plus sign is used to show that substances combine. Between the reactants and products, an arrow signifies that reactants yield or result in the following products. Let's take a look at an example involving the element copper, seen here in this bucket. Copper is often used as material for roofing and for downspouts, seen here. With time, the shiny copper metal turns green, symbolizing a chemical reaction between the copper and carbon dioxide in the air. The reaction can be symbolized by the chemical equation Cu plus CO2 yields CuCO2. In chemical reactions, the overall mass of the substances reacting does not increase or decrease. The changes that occur in a reaction involve the rearrangement of atoms, not the destruction or production of matter. This is expressed in the law of the conservation of mass, which states that mass cannot be lost or gained in a chemical reaction. The law of the conservation of mass states that mass cannot be gained or lost in a chemical reaction. Expressed in another way, the number of atoms of each element must be the same before and after the reaction. Let's look at the burning of propane, seen here. Chemical equations must demonstrate the law of the conservation of mass by showing the same number of atoms of specific elements both on the reactant side and product side of the equation. Let's take a look at a chemical reaction involving the shiny metal called silver found in this teapot. Over time, silver often becomes dirty looking, a process called tarnishing. Tarnishing involves a chemical reaction between silver and a gas in the air called hydrogen sulfide to form a substance called silver sulfide and hydrogen gas. This is expressed by the chemical equation in which silver is symbolized by the letter Ag, which reacts with hydrogen sulfide in the air, H2S, to yield or create silver sulfide or tarnish and hydrogen gas, H2. If you look at this equation closely, you will see that it is not balanced. While two atoms of hydrogen on the reactant side of the equation on the top line are balanced by two atoms of hydrogen on the product side of the equation on the bottom line, and one atom of sulfur on top is balanced by one atom of sulfur on the bottom, the number of atoms of silver, symbolized by Ag, do not balance. To do this, we need to change the coefficients. A coefficient is a number written in front of chemical elements or compounds, indicating the number of atoms or molecules of a substance present in the reaction. We can write a coefficient of 2 in front of silver on the reactant side of the equation to balance the equation. This will make 2 atoms of silver on the reactant side of the equation and 2 atoms of silver on the product side. Now the chemical equation is balanced. Now that we have explored how to balance chemical equations, let's take a look at 4 different types of chemical reactions. You probably have seen an orange coloring covering metal objects like seen here on this large iron step. This orange substance is referred to as rust, and it represents a reaction that occurs between the metal iron, as seen here, and the oxygen found in the air. The combining of iron and oxygen is an example of a synthesis reaction. A synthesis reaction occurs when 2 or more simple substances combine to form a more complex substance. The chemical equation for rusting is the following. Iron, symbolized by Fe, reacts with oxygen to form FeO2, or iron oxide. This rotting tree log is undergoing decomposition, which is the process of breaking down. This process occurs in many chemical reactions in which a substance is broken into simpler substances. This is called a decomposition reaction. In a decomposition reaction, a substance breaks down or decomposes into 2 or more simpler substances, the opposite of a synthesis reaction. When electricity is applied to water, it may undergo a decomposition reaction, producing bubbles of oxygen and hydrogen gas. In some reactions, it is possible for an element actually to replace an element in another compound. Here, the copper in the blue solution replaced the iron coating on the nail. In a single replacement reaction, atoms of one element replace atoms of another element in a compound. For example, when copper wire is placed into a solution of silver nitrate, over time the copper gradually replaces the silver in the solution, forming a blue copper nitrate solution. This single replacement reaction is represented by the equation Cu plus AgNO2 yields CuNO2 plus Ag. In other reactions, it is possible for atoms in 2 compounds to replace each other. A double replacement reaction involves atoms in two different compounds trading places with each other. Here, silver nitrate is mixed with potassium chloride, causing the potassium and silver ions to trade places with each other, resulting in a double replacement to form two new compounds. In this equation, notice how the silver, Ag, bonds to the Cl, and the potassium, K, bonds to the NO3.